Hello, welcome back to a new video. In this video, we're going to talk about the request lifecycle in vLLM. So vLLM has conceptually two main things. It has the kind of web server, this fast API thing, and then it has this core engine. So what happens is when you first send a request to vLLM, it goes through this HTTP server. It does tokenization, it does validation, it registers the tokenizer, and then it sends this request to the separate process, the separate engine called this engine core. And what this engine core does is it gets the request, and then it itself queues the request into its own engine queue. And this engine is very much similar to like a game engine that has just this core loop that calls this process engine step over and over and over again. And what this process engine step does is it has the schedule. And what the schedule is doing is it's kind of managing all of the requests. And it's doing this continuous batching. So at any point in time, there's a group of requests that are quote unquote running. And these requests are going to be either prefill or decode. They're going to be together. And for the prefill, we basically do this calculation, which is, how many tokens did we expect to have to prefill, and then how many have we prefilled so far, and then that's how many tokens that we'll need to generate this time around. And then we're going to do the minimum of that versus our token budget. So if our token budget is sufficiently small, we won't actually do the full prefill. After we calculate all of this, we then allocate KV cache blocks for these new tokens, and then we subtract the tokens that we plan to calculate from our token budget. And then we continue to do this over and over again. Now, when a new request comes in, it's at first it's going to be waiting. And what is it going to do? So the first thing it's going to do is going to do prefix matching. So as we talked about last lecture, a lot of the times in these LLM inference use cases, you actually have shared prefixes like system prompts. And so you can do this find longest cache hit prefix matching algorithm, which is this hash based algorithm, to basically see like, hey, can I reuse a block that has the exact same data for my request? We calculate the number of new tokens, we allocate new blocks accordingly, and then we move the request from waiting to running. So once we have this like next batch ready, we're ready to execute the model. So this dispatches to this GPU model runner. And what does the GPU model runner does? It updates the state. So what does it do? It adds the new requests, it removes the finished requests, and it updates this num computed tokens per request. We prepare inputs, so we basically build our input IDs, positions, load indices. This corresponds basically to the exact same signature as the forward method of the model. We do these like token position calculations, the slot mapping calculation, and we do this so that for our kernels, our flash attention kernels, we need to pass in this metadata. And so after we calculate, we build this attention metadata. And then lastly, we need to actually create tensors that we can run through this model. So this preprocess builds the tensors. And then we run it through the model. So this is just your classic Torch compile, PyTorch model.forward. But what's interesting is within the transformer layer, as we've seen in other lectures, we actually do these KV cache updates so that when we generate this new QKNV, we can update the cache. And then of course, when we're doing the attention operations itself, we are reading from the KV cache. So after we run through the transformer, we get our logits. And then we sample the tokens. So there's various sampling methods. You might have like some structured sampling. For example, you might only want to sample things accordant to like a JSON schema. There's also parameters like temperature, top K, etc. And so vLLM handles all of this in its sampling logic. Once it's done, it gets out of the model runner code back to the engine core. For each request, we append the generated token IDs to the request. We check to see if there is the stop condition Typically it's this EOS token, but it could be other things as well. If it's not finished, we update some metadata and we keep it in the queue. But if it is finished, then we free the blocks. But we free the blocks taking into account this like prefix caching thing. So sometimes we might not always free the block. Then we remove the request from the scheduler, and then we send it back over ZMQ back to the web server process. So the web server gets the output, it does the detokenization, it builds the HTTP output, and then it sends it back. And then remember, like this HTTP thing, it is also taking care of the streaming back to the client, etc. So yeah, at a high level, that's kind of the day in the life of a vLLM request. Hopefully this was interesting. We're gonna talk about SGLang next. So we'll see you in the next one.